Hello, students and YouTube viewers. Dave Soriano, and I'm a chemistry professor at University of Pittsburgh's Bradford campus in Western Pennsylvania. I'll be teaching Organic 1 lecture and Organic 1 lab via remote education this summer due to the pandemic. For my students, I have shown you the six-membered ring dynamic, cyclohexane, chair, equatorial axial ring flip. And the importance of studying that, I'll try to utilize a structure we've all heard of, lysergic acid diethylamide, or LSD. Now, Professor Nichols, Dave Nichols at Purdue University, has spent a significant portion of his career investigating LSD, its conformations, and its binding to the serotonin, the serotonin sub-receptor. A number of years ago, I actually gave a talk on some conformational aspects of LSD, both in free base and in protonated form. Now, LSD is a rather rigid molecule, but there's a couple of points of flexibility which certainly are important in trying to establish the bioactive conformation when it binds to the serotonin subreceptor. Henderson-Hasselbalch, the familiar buffer equation, would indicate to us, based on the pKa of the nitrogen, the basic nitrogen, certainly for beginning students, not the amide portion. I'll show you the structure in a minute. The amide is non-basic due to resonance. The unshared pair on the nitrogen is not available for a reaction with a proton. But there is a nitrogen in the ring that is basic. And at physiological pH in humans, 7.2, Henderson-Hasselbalch buffer equation would tell us that about 3 out of every 4 nitrogens are protonated in the blood with the LSD. Now, does this matter, whether it's free base or protonated? Yes, because when you do the calculations to do molecular modeling, we actually established a while ago and did work shortly after Dave Nichols published some landmark work in the Journal of Medicinal Chem, that if the LSD is protonated, the conformational preferences will change due to having that proton on the LSD's nitrogen. So you have to model the LSD both free base and protonated, because you don't know when it's bound to the sub-receptor, the serotonin sub-receptor, whether it's in protonated or free base form. So you have to model both. Now, what we did was to model LSD protonated, and we examined various conformations and determined their theoretical energies, heats of formation, by using semi-empirical methods, AM1 and PM3. And for the protonated form, we examined it in a solvation environment, in a water environment. And then we modeled it as free base in the gas phase, which is equivalent to a nonpolar environment. Now, if you want your heats of formation for small organics like LSD, you're going to use ab initio or semi-empirical methodology to compare relative heats of formations. In other words, delta H's. If you're working with large molecules like proteins, well, you'll use molecular mechanics, which can give you reasonably good angles and lengths and torsional or dihedral angles. But you wouldn't try necessarily to be calculating heats of formation on a protein, particularly with a PC. So, in other words, small organics, drugs, drug candidates that bind to receptor sites, if you're going to have a given conformation and you want to compare it to another one and compare their relative energies, you have to basically freeze the molecule and then carry out an AM1 or PM3 semi-empirical quantum calculation. Anyway, my viewers here presumably are at a beginning level. There may be even some professors watching this, because they may take a sentence or two that I provide and modify it for their own purposes. So let me call up, I'm in Sci-Gress platform. I already built the structure in 2D using MolView, which is in the public domain, open software. I converted it to 3D. You got to watch the stereochemistry. There's a couple of chiral carbons there. And I saved the 3D file as a .mol, which Sci-Gress will read. Sci-Gress platform is excellent, but it does not do 2D sketches. You see, you have to build in 3D, and that might be a little too much for beginning students. It's better to go with a carefully drawn 2D structure, examine, make sure your chiral carbons are established correctly, and then convert it to a 3D. So anyway, let me call it up. I'll just open a pre-existing file. And then what I'm going to do is file new object. Every platform is a little different. And I use wave function Spartan. I use ChemDraw. I use Sci-Gress. Okay, molecule, okay. And then we're going to import the file. And I'll put down MDL files, MolView. That's how I save the LSD. And there it is. Now, what you may want to do, see, there's a chiral carbon right there. 4 different groups attached. So you have to make sure you build that properly. And then my point is, when you study the 6-membered ring, cyclohexane, you might say, what's the relevancy of this? Why am I studying this? Well, now you see you have a 6-membered ring right here. And there is a double bond there as part of this aromatic ring. This is an indole heterocycle portion. But here you have a 6-membered ring, and it can't be a perfect chair. There's going to be planarity here with the double bond. And here's another ring, a 6-membered ring. Double bond in there, and a nitrogen, which has attached to it a methyl group. Right now, in that ring, as is, I had actually minimized the energy in MolView to get a reasonable structure to begin studying. Right now, this implies, this is the free base. I did not model the protonated nitrogen here, that's basic. Here's your amide nitrogen, the LSD diethylamide. That is a non-basic nitrogen. See, that unshared pair is tied up in resonance with the carbonyl group. But here, with this nitrogen, that methyl group right now is in a pseudoaxial position, and the unshared pair not shown would be in a pseudoequatorial position. Now, my point here is that you're very quickly going from fundamental cyclohexane to a fused cyclohexene system here, and here a heterocyclic 6-membered ring, cyclohexene. Now, let me show you what you might do when you begin to start to model compounds like LSD. We're going to first do an experiment, and we're going to, well, first of all, I'll beautify this. This is jargon within Sci-Gress. And it basically just cleans it up a little bit. It's good to go. Experiment, run. And I'll just click OK. Now, this is what we're going to do. We're going to do a chemical sample, conformations. Okay. We're going to generate a community, I'll call it, of conformations of LSD free base. We're doing molecular mechanics now. Standard procedure. But I'm going to go for conformations from dynamics, molecular dynamics. Now, MD or molecular dynamics has been used by physicists since about 1950. And now that we have it, an algorithm for it and established, most modeling programs will offer molecular dynamics. To make a long story short, beginning students, you start at absolute zero, 0 Kelvin, and you bring it up to 298. Now, you're not going to look at a medicine at 500 degrees Celsius because there's no person going to be taking a medicine at that temperature. So you may start at 0 Kelvin and bring it up to 298, even 350 Kelvin, and generate a pool of conformations. What kind of conformations can we have? And that's what we're going to do right now. So I'm going to start. And this is running. I'll X this out. There. Now, ChemDraw, which I use, ChemDraw will generally, I'm trying to X that out. It doesn't want to go. ChemDraw, which I use, also does molecular dynamics, but it does not portray data the way Sci-Gress does. I happen to like this Sci-Gress approach. Now, these all represent various conformations for LSD. Now, we can have play speed here. And I'll just play. Now, notice right now it's at, see the vertical line? It's at 284.3 kilocal per mole. And the lower the energy, the more stable the molecule. Now, I want to point out to you. First, let me run this. Let's just watch. Now, you can see we're generating, see the vertical line moving. We're at 210, 236. There's a 168. The lower the energy, the more plausible the structure. According to the Boltzmann distribution, you plug in a temperature, and you can actually, with the Boltzmann, looking at a difference in energy between one conformation and another, you can calculate the percentage of each at equilibrium. The Boltzmann distribution is very important in conformational analysis. Excuse me. Okay, well, you can see we're generating structures. Let me stop this. And what I'm going to do is quite arbitrarily go in here fishing around and grab a low energy one. See, these are high energy. Let me just grab this one. That's at 216. 188. Let's stick with that one, 188. Now, that's a relatively low energy one. Now, let's rotate it around, take a peek, and examine it. Now, these two rings, the so-called aromatic ring, I cover aromatic chemistry and organic too. I use a McMurray right now. And this indole heterocycle is essentially planar. Now, you can notice this ring, because of a double bond here, there, and there, this is a pseudo chair. See how these 4 carbons are coplanar? Now, we talk about flap up and flap down when you examine LSD, but we just want you to develop a feel for the ring. Now, you see that ring, and right now, this carbon is pointing up. Now, over here, this is called flap down in this ring. That carbon with 2 H's is pointing down. Nichols refers to that as flap down conformation. You can see that in that case, the methyl group is in a pseudo-equatorial position. The lone pair not shown would be pseudo-axial. But my point here really is that you're very quickly going from cyclohexane to a real situation where 6-membered rings can be found in a complex structure like LSD. Now, notice also, with this particular conformer at 240.518, or whichever one we pick, let's grab one here. Okay. Any of these could be picked. I'll X that out in a minute. My point is, any one of these conformers generated by molecular dynamics, you can save it, freeze the conformation, and determine with semi-empirical AM1 or PM3 the heat of formation for that conformer. So it's okay to generate these by molecular mechanics within molecular dynamics, but then you would take ones of interest to you, maybe some very low energy ones, very high energy ones, and very patiently freeze each one and determine the heat of formation, and then compare those. And they'll be more reliable thermodynamically. And that way you can try to establish, according to AM1 or PM3, which is the global minimum for free base LSD. A global minimum being the lowest energy conformer. Now, your bioactive shape is not necessarily the lowest energy conformer, but generally it'll be a few kilocal per mole above it. And researchers generally will start to eliminate any conformers that maybe are 10 kilocal per mole or higher off the global minimum, because the postures, let's call them, the conformations, are just so high energy they're unrealistic. So normally you're going to be working around the global minimum or a few kilocal above. And then you begin to investigate them. Then at a higher level, if you have an X-ray photograph of the serotonin sub-receptor, and Professor Nichols is doing this, believe you me, I watch his work at the Protein Data Bank, you will actually look at an X-ray image or an NMR where the LSD is bound to the serotonin sub-receptor. And that way you can begin to do docking experiments to try to see how the fit occurs between the protein and the LSD ligand. And generally, I'm not going to give you the reference right here, but there's a pretty good scientific reference that when you look at an X-ray solid state of a compound, a conformation in the solid state, let's say an X-ray of LSD, free base, generally that's going to be pretty close to what you might see in a bioactive conformer. Because the crystal packing, there'll be a little bit of distortion, but normally it's a low energy. So when you're looking at an X-ray of a compound like LSD, what you're seeing there in that solid state should be reasonably close to what would be the bioactive conformer. And that can be confirmed, of course, by looking at Nichols' X-ray image of the LSD bound, and then compare it to the X-ray of the LSD on its own in the crystal state. The main purpose of this video, though, is to show you that you study diligently the six-membered ring flip, pseudoaxial, pseudoequatorials for 5 and 4-membered rings, classic equatorial axial for cyclohexane, and then 6-membered rings with a double bond in the ring, like you're seeing right with this ring here. And we bring that up and you can see you basically have 4 carbons coplanar, 1, 2, 3, 4, because of that double bond, 120 degree bond angle. You know that these 4, 120 degree bond angle, and the dihedral angle will be 0 degrees or close to it, because of those sp2 carbons. And then that 6-membered ring has 1 carbon down and 1 up out of the plane of the other 4. So there's the 4, and then 1 down, 1 up. Then you can also investigate the 6-membered ring with nitrogen and the position of the LSD. Is that carbonyl oxygen in red pointing in toward the ring or away from the ring? This is also this is your introduction to molecular modeling, and you go from a fundamental chapter in organic to a high-level area of research very quickly, but you have to know your fundamentals. Hey, thanks for listening. Bye for now.